Okay, so what we're going to talk about these protein separations by gel electrophoresis. We have two methods. Only the first method in our syllabus. Second method is not in our syllabus. So this one is just for your informations only. Okay, but I will explain why I talk about this method. Okay, so now the first method also is known as the sodium Dodecyl sulfate polyacrylamide gel electrophoresis. In biology, we always term it as SDS page. Okay, so it's again page is a polyacrylamide. So to separate the protein, we use the gel, not agarose gel, but polyacrylamide gel. Okay, so but this gel also included another item in the gel called SDS, and it's very important to know why SDS is included. But in the DNA, we don't use SDS at all. Okay, so before we start, we're going to look at this principle of the SDS, why we include the SDS. So this is a method. SDS page is commonly used to separate protein. Highlight, guys. We are not, okay, we separate the mixture of the protein. Like for example, in a cell, we have so many kind of proteins, so many kind of enzyme. How we can separate them? We want to separate them based on their molecular weight. Okay, so means that if we put in terms of the common sense in this case, we know if the molecular weight higher, larger, it tends to move slower. If molecule small molecule or small protein tends to move faster. So in this electric field, we are going to have the differential rates, movement difference. I mean, how fast the movement. So it means that the movement of any charged particle through the electric field is determined by these two items, net charge, whether they have charge or not. If they don't have charge, they stay lah, right? You try to imagine that I don't have any charge, so I won't move to the positive end, I won't move to the negative end. And also the molecular length or molecular radius here. Okay, so normally in DNA, we don't have this problem. Why? Because DNA, they are negatively charged. And DNA in terms of the shape, they are linear. Even though they are double helix, but generally, relatively, they are linear. So it means that the molecular length will be molecular weight dependent for DNA. If I have more nucleotides, it becomes longer, right? But protein special. Why? Protein first. In terms of molecular charge for protein, it can be positive. It can be negative. It can have no net charge. Don't say no charge, no net charge. Okay, it depends on the R group of the amino acid. If the R group is positively charged, more positively charged R group compared to negatively charged R group, then the proteins will be positively charged. If the proteins have more negatively charged R groups, definitely the net charge of the proteins will be negative. Or if let's say positive charge and negative charge are in equal number, then it becomes no net charge. Are you clear? So it means that net charge will be the problem now, the migration. Okay, so some will migrate to positive terminal, some will migrate to negative terminal, and no net charge, they cannot move at all. Can I see that? Okay, next. So, and also in terms of the shape, proteins, they are folded protein. So means that you try to imagine, when you walk, you person, okay, you walk in a crowded region. You try to imagine you open your hand, big, okay, open out your hand. When you want to move in the crowded regions, you tend to move slower. Cannot, because of resistance and people here and there. But if you try to close your arm, put it nearer to your body, easier for you to pass through. Cannot. But you realize that something, molecular size, in terms of molecule, you are same size, right? It's not like, okay, I put my hand, then my size larger, and then I close my hands, my molecular weights become lower. No, the same. But the thing here is because of the folded proteins, and also compared to the what we call this another protein, which is fibrous protein, which is non so folded. Then you can see that even though they have the same molecular weight, they can't be separate. Okay? They're same molecular weights, but the rate of movement will be different. So it's not really weight dependent now. Okay, so understand the concept here. Protein, we need to have a special step because of the folded protein, and it determines by the amino acid compositions, the sum and of the positive and negative, and also depends on the tertiary structure, whether they are folded or fibrous proteins. Okay, if the globular means that it tends to be more round and less resistant, but if they are fibrous protein, then it tends to be longer, linear. Okay, so in the protein native stage, the different protein with the same molecular weight may migrate at different speeds. Can you see that? They are same molecular weight, almost the same, but they have a different speed because of their charge and also their precise three-dimensional shape here. So to overcome these two, net charge problem as well as the molecular radius problem, what we're going to do here, we have to treat the protein by using the SDS. This is the chemical, the SDS. So what's the function of chemical? Here, this chemical will disrupt the tertiary structure of the protein by reducing the folded protein down to linear, means to make them unfolded. Can you see that? We make them unfolded. And after unfolded already, they will coat the protein with a uniform negatively charged, okay, a very uniform negatively charged. So in this case, we solve two problems already. So no matter what kind of protein, whether they are positively charged protein, negatively charged protein, or no net charge the protein, we always coat them with a negative charge. So it means that now all protein become negatively charged already. That's one. Okay, because of this SDS. Second, this SDS also help to denature the proteins, make the protein become linear. Are you clear? And then the SDS bind fairly uniform to the linear protein, meaning that the charge of protein is now approximately proportional to the molecular weight. So try to imagine you coat it with negatively charged, okay, SDS. So the longer the protein, your charge will be more. Can you see that? Are you clear? Okay, the longer the protein, the more negatively charged that. Okay, so SDS also present in this polyacrylamide gel. So it means the gel, to make sure that once protein are linearized, they won't, when they pass through the gel, okay, they won't lose this SDS. Are you clear? It's something like friction, right? Try to imagine your body coat with a layer of powder. When you go through crowded regions, then there's this powder may lose, right? But you try to imagine if everyone also coat with a powder, then this powder, some sort of, can stick on your body. Okay, so because they are negatively charged, they will move to the positive terminal. Depends on their molecular weights. So don't worry about this, guys. This methyl ethanol is the one that actually make to cut the disulfides. Okay, I don't have the battle because the battle diagrams, but basically, can you see that I have two proteins here? One is the what we call this tertiary protein with one polypeptide chain here. Can you see that folded with negative, positive, and disulfide bond? Okay, so I have second protein. I have second protein here. You can see that is a quaternary protein with the disulfide bond. Okay, so in the process of treatments, we put in the SDS. So SDS is going to coat my protein with a negatively charged. And we also put in another item called methyl ethanol. Methyl ethanol actually is the one that cleave the disulfide bonds. Can you see that? So in this case, even though I cleave the disulfide bonds, make it linearized, I only have one fragment. So that's why one band. And it's a longer one. Can you see that? So one band near to the sample loading well. But for the protein number 2, SDS also coat them with make it linearized. But because of the presence of the methyl ethanol that break this disulfide bond, I'm going to have two bands, and these two, they are smaller, okay, almost the same size. So that's why it appears somewhere here, okay, further away from the band. Okay, so once the protein are in the running gels, they are separated because a higher molecular weight protein moves slower and through the porous polyacrylamide gels than the lower molecular weight. So again, similar to the DNA, they will move faster if they are smaller fragments. Okay, so can you see that? Longer fragments, it will be trapped in these polyacrylamides, but shorter fragments actually can move further. Okay, So I stopped here. Tomorrow, we're going to continue with visualization of band using the Western blots. Previously, we talked about the Southern blots. Southern blots because we use the DNA probes, okay, to look to visualize the DNA, because DNA, they are colorless. Same goes to the protein. Protein also colorless. When a protein, they are colorless, how we can detect them? Okay, so this one we're going to link it back to your ES topic, monoclonal antibody. Methods is almost the same. Okay, so tomorrow again we'll continue with isoelectric focusing. Okay, and then we're going to enter to another part called microarray, and I want to complete the bioinformatics also tomorrow.